All right, so let's go through another online lecture in complex analysis. This time going through section or subsection 323. Cauchy theorem for a certain kind of sets. So as I said, most of the time we'll be looking at sort of what kind of sets or what kind of path we get Cauchy theorem for. So this is Cauchy theorem where the set in which the function is defined is star-like. So what is star-like, right? What is this? Let me move to what is this star-likeness? Or sometimes star-like with respect to a point. So there's going to be, there's some specific point in the, let's just say a domain usually. That's what we'll be interested in. But it's really for any set in the definition. So it's star-like or star-like with respect to a point if you want to emphasize with what point. So some fixed point in U. If every segment from this fixed point to any other point in U, the entire segment is in U, right? So it's sort of like convex, but instead of every segment between any 2 points, here we're saying, well, we're going to have it's sort of almost convex while keeping one of the points fixed. That's really sort of this definition here. So this is the picture, right? So we have some some kind of central point. It doesn't have to be sort of central in any way, but some point and every other point can be connected inside this set U by a straight line. And there could be many other such Z knots possible, but there's at least one. Now notice this is not a convex set, right? Because for example, between this point over here and this point over here, the straight line segment doesn't lie in the domain, but between any point over here, there is a straight line segment to Z naught that's in the domain. All right. So convex set in particular is going to be star-like because, well, you're asking more for convex sets, but there's more star-like sets, and the name star-like, I drew it to sort of look kind of like a star, but it doesn't really have to. But something that looks like a star is going to be star-like, but lots of other domains will be star-like. So, all right. So a proposition that will need to say something about Cauchy is how to, if you've remembered, we had Cauchy for, if a function had an antiderivative, if you have a primitive, then we had a Cauchy theorem for it, that it was the integral around cycles was 0, right, for such a function. So, well, let's see, when do we have a primitive, right? So suppose that we have in an open star-like set. This is going to be a domain. If it's star-like, it's going to be connected, right? Because it's path connected. Every 2 points can be connected by, a couple of straight line segments, right? You just go to Z naught and then go to the other point, right? So it's going to be a domain. Suppose it's star-like. And let's suppose that we have a continuous function, right? Continuous so that I can write down its integral. And let's suppose that that we get that the integral around the outside of the triangle is 0 for every triangle that lies in U. And remember, what we meant here was that the entire triangle lies in U, but we'll see that for star-like, it's sort of automatic. So then will have then have f has a primitive, right? It means there exists a holomorphic capital F whose derivative is little f. Right? So let's prove this. Suppose U is star-like with respect to some z0. Right? And let's just write down this antiderivative. Just write it down as a function. F of z, capital F of z, right, is just the integral along this interval from z0 to z, right? Now, consider any sort of disk around z of radius r that's still in U, right? So it's an open set. There's always something like that. And basically, let's look at a small, let's go somewhere else in the disk, right, from z. So it's centered at z, and we're moving, a little bit off, right? So h is something of size at most r, right? So we're looking at z plus h, a point nearby z, right? Still in this disk. So, here you have the picture, right? So you have the z over here. You have this little disk, right? And you have at this point z plus h over here. Maybe got rid of the too much color there, right? So that's what we set up, right? This is where your z0 is, right? Somewhere else in the domain, right? Now, if I look at the triangle that's has these 3 points as the vertices, because U is star-like, right? I mean, this segment, the segment between z and z plus h, right? This segment over here, that is clearly inside this disk. That's in U, right? Just because that's how we pick this disk, right? For any age such as this, right? And then we have that every line from z0 to any other point in U, so in particular, maybe 2 points on this line over here, well, those are all also in U, right? So that means that this entire triangle, including the inside, right? Again, over here, we're talking about the inside. So this is where we're looking at the boundary. This is where we're looking at the inside, right? Inside and the boundary, right? You're talking about the closed triangle, the convex hull of the 3 points. All right. So we have that this triangle is completely in U. All right. Now, what was the hypothesis? The hypothesis was that around every triangle, the integral is 0. Now, we could write it in this way, right? We're going from z0 to z, from z to z plus h, and from z plus h to z0. And I'm going to write it as minus z0 to z plus h, right? Traveling in the opposite direction. Remember, this is the chain arithmetic for these paths, right? I mean, that just means that I'm integrating first around z0, first in the, along the path z0 to z, then from z to z plus h, and then I'm subtracting the integral from z0 to z plus h, right? So that's the same thing as integrating around this triangle. And we're saying that that's 0, right? That was the hypothesis. All right, so we're trying to figure out that this capital F, right? The one that was, defined over here, right? That guy is our antiderivative. So let's compute its derivative and see that its derivative is little f, right? So, well, how do you compute a derivative? Well, look at the difference quotient, right? So we look at the difference quotient over here, and we write it in terms of the integral, right? So it's this integral over here minus this integral over here, the whole thing divided by h. I'm going to write it as a single integral, right? So it's the integral from z to z plus h minus the integral from z naught to z, right? And I'm also dividing by h, right? So that's what the difference quotient is in terms of an integral. Now, this is where I use that the integral around the triangle is 0, right? We get, it's really, I guess, with a minus sign over here, right? But I have z naught to z, z naught to z plus h, right? The signs are opposite, but it's okay, right? That means that this integral over here is equal to this integral over here, right? This is equal to this, right? Just from looking at the integral around the triangle. All right. Well, so now I have an integral. Now it doesn't really matter where z naught was, right? We've gotten rid of the z naught, right? That's sort of the point. And we have we have this. We just write down the integral, right? We write down just standard parameterization of the line segment, right? Using t from 0 to 1, let's say, right? So it's z plus th, right? The derivative is h. That's why I'm getting this h over here. But at h, it's nice. It's sort of it cancels out, right? Really nicely. So what do I have? It's this. Now, really, I can sort of stop here. You should be able to recognize that the limit of this thing as h goes to 0 is f, right? I'm really just looking at the average of this function inside, right? That's what this integral is, and as h gets smaller and smaller, right? The average on a little on the little interval from z to z plus h, well, that just goes to f of z, right? Now maybe another way of seeing it is seeing that this inside, that goes uniformly as h goes to 0. The inside goes uniformly to just the constant f of z, right? So I can pass that inside. Now, we could, to be more explicit, we could just write down this inequality, right? Say, what are we trying to do? We're trying to write down this thing, right? So this is kind of a neat trick. So let's go through it, right? I mean, if I want to show that this integral, right, equals this, equals f of z, well, I need to get something under. I just want one integral to estimate. I need to get this f of z inside that integral. Well, but the integral of 0 to 1 of the constant f of z, right? Well, that's just f of z, right? So I can write it as an integral from 0 to 1 of f of z, right? That means that that we're getting, let's see, right? That means that I can just push it, I can write it as one integral, right, of this guy, right, this guy minus this guy, right, in terms of t, and then I can push the absolute values inside by the triangle inequality for integrals, right, and I get that the estimate is this, right. Now here, right, as h is small because of the continuity of f, I can bound this above by some, by any epsilon, once I make sure that h is small enough, right? So picking some epsilon, make h less than delta, and I have that this is with an epsilon, right? Just by continuity of f at z, right? So that's what we have. Well, that's exactly what it means for f prime, capital F prime, to be little f, right? At any particular z, right? All right. Now, previously we proved Cauchy-Goursat, right? Which was this. That is a very powerful result. It doesn't seem that powerful, but it's basically Cauchy for triangles. But again, it's the point is that and really why it's called Goursat is that it's not just the Cauchy theorem, right? It's when do we prove it in the development? It was only assuming that f was holomorphic, meaning it was only assuming that f was complex differentiable. It didn't assume anything about the derivative, right? So if f is holomorphic, if it's complex differentiable around every point, then the integral around triangles that are completely in the domain, is zero, right? So using that, we can now use the proposition, right, to prove a corollary, right? It's a corollary of the proposition, and really Cauchy-Goursat, so there's a consequence of Cauchy-Goursat is that if we have an open and star-like domain U and a holomorphic function defined on U, then this holomorphic function has a primitive, right? Then it's the derivative of some other holomorphic function defined on U, right? So now we can write down this Cauchy term for star-like domains that we said, that's this subsection is about. So if I have an open star-like U, I have a holomorphic function f, and I have a cycle gamma in U, meaning something equivalent is changed to a bunch of closed piecewise C1 path, right? That's what we defined cycle to be. Then we get that the integral around that cycle is zero, right? So it's no longer about some triangles or something. It's really about any cycle, right? And the point is that we're not trying to sort of make this cycle and sort of approximate it by triangles or some other nonsense like that. Now you use the triangles to define an antiderivative. Once you have an antiderivative, once you have this primitive f, this capital F, right, then you can use basically fundamental draw of calculus, right? So that gives you the sort of the Cauchy theorem for derivatives, right? And so once you have that, you know that around any cycle, the integral is zero, right? Because once you have a primitive, right? So it's an immediate consequence, right? So it sort of, it might not be maybe the most straightforward way of getting that, because so we have Cauchy for certain paths, but instead of then kind of trying to generalize the paths in some way, we say, well, we're going to use those certain paths, which are just triangles, to get a primitive, and then then we can do it for any path, right? So once you get it for triangles, you get it for any path, really, right? That's basically the idea here. All right. Now, maybe a remark about something that you've probably seen in vector calculus. So if I have a complex valued function on in R2, right? Well, or in C, right? It's really an R2 valued function on R2, right? It's a vector field, right? And in vector calculus, you prove basically something like, if I have an irrotational vector field, meaning it satisfies some curl, conjugate curl is 0, right? It doesn't rotate stuff. Sort of should look familiar now. So if I have some irrotational vector field, then on a star-like domain, right? Then it's a conservative vector field, right? And again, there has to be some condition on U, right? This is not going to be true in any U, just like here, right? So it means there is some real valued f whose gradient is this irrotational vector field. And this is actually, this is sort of the in some sense, the more general version of what we just proved. And you could think of it as you can use, if you have this statement over here, this theorem over here, you could prove the other, what we just proved by massaging everything in the right way. But really, the proof is exactly the same. You do exactly the same thing. You define this function whose gradient is supposed to be in the same way, really, using line integrals, right? And you can use again these triangles. So it's basically the same thing. So all right. So let's stop the recording.